In today's video, we're going to be talking about Newton's universal law of gravity. After watching this video, you should be able to use and apply Newton's law of gravitation to various problems that may be presented to you in homework assignments, quizzes, or tests. So let's get right on into it and take a look at this formula. So the law of gravity basically applies to everything. It's not just people on Earth. It goes all the way, out into the universe and beyond. Okay, if there is anything beyond the universe. So basically, how this law came about was Newton compared the acceleration of the moon to the acceleration of objects on Earth, believing that basically gravitational forces are responsible for basically causing each to fall towards the Earth. So believe it or not, all objects are attracted to each other with a force of gravity. Okay, so you're right now attracted to the computer screen or the phone that you're watching this video on through the force of gravity, which is strange to think about, but it's true. Even though it's a very small force, it is there. Okay, so gravity truly is universal. Basically, it's everywhere. Just to what extent is the force being applied to you kind of varies based upon your distance. Okay, so this is the formula that we're looking at right here. Basically, it says the force of gravity equals big G times the mass of object 1, which in many problems will be the Earth, times the mass of object 2, which will be like the thing that you're comparing it to, whether it be a spaceship, a person, an apple, whatever, divided by the distance squared. Couple things to kind of keep in mind as you're doing this. These distances need to be this must be in meters. Okay, so if they give it to you in kilometers, you have to convert it to meters. And the reason why is this big G is a constant, and it's measured in Newton meters squared over kilograms squared. So you have to basically have your distance in meters and your masses in kilograms. Okay, if you don't, just convert it, change it so that it is, and then everything will be peachy. So what is this big G? Well, that's something we're going to talk about in the very next slide. So before I get into what big G is, I'll just move to the next slide. But do make a note of what the number, or the value of big G is. 6.67 times 10 to the negative 11th Newton meters squared over kilograms squared. And basically, this big old list of units here is all going to get canceled out, so you're just left with newtons, because that's what force is measured in. So if you look at the math and the formula itself, you'll see how all the units cancel. But big G is a very small number, 6.67 times 10 to the negative 11th, if you start to look at it. So the question becomes, what is the difference between little g and big G? Because notice that in previous problems, like let's say you're trying to calculate the force of gravity, we always say, well, the force of gravity equals m times little g, which is true, that is correct. Little g is the acceleration due to gravity, and on Earth it's 9.8 meters per second squared. If you go to a different planet, we're going to be talking about a different little g. So this formula is still valid. This big G here is just a constant. It's just something that is thrown into the equation to basically make it work. And it's a really small number. Now, you don't need to remember all of this. I would just worry about this to only 3 digits, 6.67 times 10 to the negative 11th. So that's basically the difference. Little g, and so don't let that confuse you. Little g is the acceleration due to gravity, and typically it's going to be on Earth. And big G is that constant. Okay, so do not put 9.8 here. Okay, don't do that. Okay, that's a no-no, because that's not the G I'm looking for. I'm looking for this G here, 6.67 times 10 to the negative 11th. Okay, let's continue on our journey. So gravity is universal, and basically it interacts between all objects with an intensity that is directly proportional to their masses. So notice their masses are in the equation along with distance. Okay, so those are the only two factors that really affect how strong the force of gravity is between two objects. So as I mentioned earlier in the video, as you sit in your seat watching this video, you actually are gravitationally attracted to the computer that you're watching this on, or your phone, and even if your physics book is in the near vicinity, you're actually attracted to that. As hard as that may be to believe, in terms of gravitational attraction, it does exist. You are actually attracted to your physics book. Okay, so it's universal. It's everywhere basically. This is kind of a cool graph. that looks at the value of, now notice this time we're talking about little g, the value of little g, which is the acceleration due to gravity, dependent upon its location from the Earth's center. Okay, so I mean, like here we are, like right here, right? We're standing on the Earth, right there. The acceleration due to gravity, when we're really close to the Earth, is about 9.8 meters per second squared. As you get further and further away from the Earth, so as you travel further and further away, the acceleration due to gravity, or little g, gets smaller and smaller. The cool thing is, big G doesn't change at all. That is just a constant. It's going to stay constantly the same. But little g absolutely does change, because little g is location dependent. How close are you to the other object that you're comparing the force of gravity to? Okay, and typically that other object is going to be the Earth, okay, because the object needs to be pretty dang massive to create a gravitational force that's really worth measuring. All right, let's do some example problems where we actually kind of, apply this in a fashion that's meaningful in terms of like what I might ask you guys for like a test question. All right, so it says, determine the force of gravitational attraction between the Earth, which I can tell you the mass of the Earth is 5.98 times 10 to the 24th kilograms, and a 70 kilogram physics student, if the student is standing at sea level, a distance of 6.38 times 10 to the 6 meters from the Earth's center. Okay, great. Well, Newton's universal law of gravitation is F equals big G times mass 1 times mass 2 over distance squared. Okay, that's basically Newton's law of gravitation. Okay, so basically I have all the numbers I need to plug in to figure out what F is, right? My G is 6.67 times 10 to the negative 11th, and I'm going to just keep the units out just so it kind of stays a little bit cleaner. So 6.67 times 10 to the negative 11th times the mass of the Earth, which is 5.98, times 10 to the 24th kilograms, times the mass of the physics student, which is 70 kilograms, all over the distance squared. And the distance from the Earth center, if you're at sea level, is 6.38 times 10 to the 6th meters, and that is squared. Don't forget to do that. That is something that I see a lot of people make mistakes on, so don't forget to do that. And if you do all that math, just throw that in your calculator, you should get a force of 686 newtons. Okay, so that's about like the average force that someone would experience when standing at sea level would be 686 newtons. Okay, now you may say to yourself, well, Vinny, what if I'm in a plane? Okay, let's say I'm flying in a plane. What would the force of gravity be on me there? Because now I'm real high up in the air. Planes, they fly, a few miles above the Earth's surface. Does that make a difference in terms of the force of gravity that I'm experiencing? So notice, basically, same problem. I'm wondering what the force of gravitational attraction is between the Earth and a 70 kilogram physics student if the student is an airplane at 40,000 feet above the Earth's surface, which I'm not going to ask you guys to convert feet to meters at the moment, but that would place us at a distance of about 6.39 times 10 to the 6 meters from the Earth's center. So again, let's plug in Newton's universal law of gravity. F equals big G times mass 1 times mass 2 over d squared. And if I plug in some numbers here, big G is 6.67, gosh darn it, sorry about that, 6.67 times 10 to the negative 11th, and again, I'm going to leave the units out, hopefully you guys are okay with that, times the mass of the Earth, which is 5.98, times 10 to the 24th kilograms, times the mass of the physics student, which is 70 kilograms, all over the distance, which now we're in a plane, so we're a little bit further from the Earth's center, right? So it's 6.39 times 10 to the 6th. And again, don't forget to square it, because that's going to change your answer if you don't square it. Okay? And if you do all this math, if you throw that in your calculator, the force of gravity on the physics student would be 684 newtons. Okay? And the reason why I do this second sample problem is to show you, notice, yes, the force of gravity is a little bit smaller. How much smaller? Well, if you remember from the previous slide, it was 686 newtons standing at the Earth's surface, and now on a plane it's 684 newtons. So we lost 2 newtons of force. That is not that big of a difference. Okay, so you really need to get further and further away in terms of distance to see a dramatic effect in terms of the force of gravity. So basically, for us folks here on Earth who are not astronauts and are not visiting like the space station or anything like that, we're probably going to be experiencing about the same force of gravity. I mean, you can climb Mount Everest and you still be experiencing about the same force of gravity. That the difference would really be negligible. Okay, that takes care of this video. I will see you guys next time.